My dear students, in my last lecture, I have discussed the welfare economy. This is basically Unit 3 of Intermediate Microeconomics 2 paper. In our analysis, we have analyzed three aspects of marginality conditions of Pareto optimality. That is the optimality condition for exchange optimality, production optimality, and the general optimality condition. And during the general optimality condition, I have used one formula, that is MRT equal to MCX by MCY. That is this formula. And some of you have asked me how we can derive this relationship. So today first I discussed on this issue, that how can we derive the formula for MRT equal to MCX divided by MCY. Now what is meant by MRT? MRT is actually the absolute slope of the production possibility frontier. Now production possibility frontier, you know that it is the locus of the different combinations of two goods that can be produced with your limited resource and given technology. And generally the PPC or PPF is concave to the origin. Now if you are at point A, then the output mix is Y2 OX1. That is, you are producing X1 amount of commodity X and Y2 amount of commodity Y. This is represented by the locus, that is the combination point A. The same is true for point B. If you are at B, that means X production increases from X1 to X2 and Y production decreases from Y2 to Y1 if you move from A to B. So B is another product mix. Now the slope of the PPC, that is, if you move from A to B, this is your del X and this is your del Y. So del Y by del X with a negative sign is the slope of the PPC, and the absolute value, that is del Y by del X, is actually MRT. Now this MRT can be shown, it is the ratio of marginal cost of industry X and marginal cost of industry Y. Now let us prove this. Now you know that what is marginal cost? Marginal cost is the change in total cost due to change in the output. So for X industry, MCX equal to DTX by DX, where TCX equal to W into LX plus R into KX. We know that this LX and KX, actually LX is the labor input used in X production and KX is the amount of capital inputs used in the X production, and W and R the respective prices of labor and capital. So this is the total cost for industry X. In the same way, we can say that TCY is the total cost of industry Y, that is W into LY plus R into KY. That is, LY is the amount of labor used in the Y production and KY is the amount of capital used in the Y production. So this is the respective total cost function. By the definition of MCY, we can write that this is DTCY by DY, that is change in total cost due to change in the Y production. Now if we take the ratio MCX by MCY, this becomes this DTX by this DY into DX. Now what is DTCX? That is the total differentiation. You just make a total differentiation. DTCX is W is constant, R is constant, so W into DLX plus R into DKX, that is written here. That is, in place of DTX I have written this. Okay. Similarly DTCY, if you differentiate this is your W into DLY plus R into DKY. Now you put this here, so this becomes this. So in place of this you can write this. Now one interesting fact is that when you move from A to B, then X production increases, Y production decreases. So when Y production decreases, then the factors released from the decrease of Y production, that I have written here, factors released from the decrease in Y production. You see, Y production decreases, so factors released from the Y industry, but X industry increases the output, its output. So the released factors are now absorbed by X industry because X industry's output is increased. That's why I have written that must be equal to the factors absorbed by the increase in the production of X. That is DLX. What is DLX? DLX is the change in labor input is equal to minus DLY. Why it is minus? Because it is released and that is absorbed by the X industry. Similarly, capital minus DKY is the amount of capital that is released from the Y industry and that is absorbed by the X industry. So in place of DLX, I put minus DLY. In place of DKX, I put minus DKY. And then I take minus as the common factor. Then it is within the bracket. It cancel out. So it becomes minus 1 into dy dx. Now what is minus y into dy dx? This is the slope of the, if you take the absolute value, it is the slope of the PPC, that is MRT, marginal rate of transformation. So what we observe, what we have achieved, that MECX by MCY is equal to MRT. That's why I have written this relationship, MRT equal to MCX by MCY. So this is our first part of my lecture. Okay, so if you have any problem, you can talk me over phone. Okay. Now the second part, that is important component of the welfare economics, that is the social welfare function and the grand utility positive frontier. And to analyze this, we consider there are two individuals, individual A and individual B, consuming two goods X and Y, and these two goods are producing with the help of two inputs, labor and capital. And we know that this total final good X is distributed among individual A and individual B. XA, that is the amount of X that is consumed by individual A. XB is the amount of X commodity that is consumed by B. Similarly, Y good is distributed among A and individual B. YA and YB are the respective amounts of good Y that is consumed by individual A and individual B. Similarly, this total labor input is distributed among the X industry and the Y industry. That is L equal to Lx plus Ly. Lx is the amount of labor goes to industry X, Ly is the amount of labor goes to industry Y. Similarly, capital is distributed among the two industries X and Y. Kx is the amount of capital goes to industry X, amount of capital Ky goes to industry Y. Now, if you consider the social welfare function is a function of UA and EB. Now what is UA? UA is the utility level achieved by individual A and UB is the utility level achieved by individual B. Now the social welfare that depends on the UA and UB. Now if you consider different combinations of UA and UB, from which you will get the same level of social welfare function, then the locus of all those combinations will give you the social welfare contour. Now if you look at the diagram, the social welfare function is represented by the social welfare contour that I have shown here. You see, like indifference curve, social welfare contours are also downward sloping, convex with origin, non-intersecting. But here, if you move along this direction, that is higher social welfare contours will represent the higher level of social welfare. But along the social welfare function, that is point A and point B, both represent the same level of welfare function, welfare level. But if you move from A to C or B to C, you will reach higher welfare level, that is represented by the welfare contour W2. So again, if you move from C to D, then the social welfare will increase from W2 to W3. So in this way, when you move along this direction, it represents the high level of social welfare function. So this social welfare function is one of the important components for optimum allocation of the resources or to maximize the social welfare. This is one of the important components that the social welfare function. Now another important component for maximizing the social welfare is grand utility possibility frontier, in abbreviated form GUPF, grand utility possibility frontier. Now what is grand utility possibility frontier? It is actually, when you consider the PPC, for each point on the PPC will get the utility possibility frontier. Now the envelope of all utility possibility frontier will give you the GUPF, Grand Utility Possibility Frontier. And one thing you must remember, that all the points on GUPF satisfy all the Pareto marginal conditions of efficiency. And in my last lecture, I have clearly discussed on these Pareto marginal conditions. For example, the exchange optimality condition, number 2 production optimality condition, and number 3 general optimality conditions. All these conditions are satisfied along this GUPF. Now let us discuss how can you derive the GUPF, that is Grand Utility Possibility Frontier. For this, we consider PPF FF dash in our economy. FF dash, we consider this. This is FF dash, that is our PPC, and these two, that is point B and point A, these are the product mix. When you are at point B, that is you are producing OY1 amount of commodity Y and OX1 amount of commodity X. Similarly, if you are at point A, then your product mix or product combination or commodity combination or commodity mix is OY0 and OX0. Okay, now considering this, you get the Edgeworth box this, and considering this, you have this is the Edgeworth box. This is now if we consider that's why I have written here product mix A and B. We have two contract curve. If you consider the Edgeworth box this, then this is your contract curve. I have already discussed in my last lecture. And if you consider this, then this is the Edgeworth box, and this will be the contract curve. That's why I have written two contract curves, OA and OB, and utility combination. Now suppose we consider the contract curve OA, that's why I have circled it. For contract curve OA, and if you consider the point C, if you consider point C, then you have two utility levels. One is for individual A and this for individual B. So for individual A, this is A2, and for individual B, this is B8. So when you are at point C, then the utility combinations is A2 B8. Okay, clear? That's why I have written here C A2 B8. This is corresponding to the commodity space. This is for the commodity space. Okay, now this commodity space, that is this point, can be mapped into C dash in the utility space that I have shown here, that is C prime. C prime is corresponding to point C in the output space. In the output space, we know that commodity space or output, we know that utility combination is A2 B8. A2 is the utility of individual A and B8 is the utility level of individual B. Now this is the utility space measuring utility of B vertically and utility of A horizontally. So this C prime represents this C, B8 and A2. Combination A2 and B8, that is corresponding to point C in the commodity space, that is reflected by point C prime in the utility space. Okay. Similarly, if you consider point G, so for the contract curve OA, for the output mix OY0X0, if you consider the point G, that means utility of individual A is A4 and utility of individual B is B3. So when you are at point G, the utility combination is A4 B3. Now this G point can be mapped into G dash in the utility space. This is represented by this G prime. G prime is corresponding to G in the output space. In the output space we know that the utility combination is A4 B3. So A4 B3 is represented by this G prime. You see, this is A4 and this is B3. Now joining this C prime and G prime, that is this curve, that is S prime. This is the utility possibility frontier. That's why I have written SS prime is the utility possibility frontier for the contract curve OA. Similarly, if you consider the contract curve OB, and if you consider this point K or H, you can correspondingly get points K dash and H dash corresponding to the output space, and considering and joining this, you will get R prime. This is the utility possibility frontier. So for each contract curve, you will get such utility possibility frontier, and the envelope of all these utility possibility curve, that is this dark line, is actually your grand utility possibility frontier. Okay, so grand utility possibility frontier is the envelope of all utility possibility frontier. That's why I have written here that the envelope of this utility possibility frontier is the GUPF. And another important point is along this GUPF, all the marginal conditions of Pareto optimality are satisfied. This is important concept. Okay. Now this GUPF and the social welfare function, these two are important tools to discuss the social optimization. Now, where social optimality is reached? When this GUPF is tangential to the highest attainable social welfare function. According to this diagram, W star is the point where social welfare is maximized. That's why it is called the bliss point. Okay, and corresponding to this UB star is the utility derived by individual B, and US star is the utility level derived by individual A. So at this point, Pareto optimality condition is satisfied, as well as social welfare is also maximized. But one thing you should remember, that all the Pareto optimality point may not give the social welfare. For example, you consider that point N, here Pareto optimality condition is satisfied. Why? Because this point N is on the grand utility possibility frontier. But if you draw the social welfare function, you will get the lower social welfare compared to point W star. W star welfare is W3, but at point A, welfare is below W3. So important point is both these 2 points are such points where Pareto optimality conditions are satisfied, because both points are on the same grand utility possibility frontier. But this point, though Pareto optimal, but may not represent, but is not representing the welfare maximization point. But another point, interesting, L, you see, that is not on the GUPF, it is within the GUPF. So Pareto optimality condition is not satisfied here. But if you consider N and L, then L is better than N, although L is not Pareto optimum. Why? Because L represents higher welfare level W2 compared to N, where the utility level is below W2. So this is a strong point where we can say that Pareto optimality condition is necessary but not sufficient condition for welfare maximization. Like perfectly competitive market, we have already discussed in my last lecture that perfectly competitive market is necessary but not sufficient for Pareto optimality, because in case of perfectly competitive market, automatically all prices, that is price of goods, price of factors, all are constant. That's why automatically the equality condition, that is MRS equal to Px by Py, MRT equal to MCx by MCy, all are satisfied. But if you have the externality problem, if you have the public good, existence of public good, if you have asymmetric information, then it can be shown that if you have externality, then it can be shown that even if you have perfectly competitive market, then Pareto optimality will not be reached. So two things you must remember. Number one, perfect competition is necessary but not sufficient for the Pareto optimality. And today, from this diagram, you can definitely say that Pareto optimality is necessary but not sufficient for social welfare function. Okay?